This is Lesson 10 in our Calculus 2 series, Integration by Parts. In the next several lessons, we're going to be building on the integration tools you learned in Calc 1. So let's take a look at our basic integrals. We have x to a power, e to the x, sine x, cosine x, a to the x, 1 over x, secant squared, sinh, cosh, and the basic integrals from arcsine x and arctan x. We also learned in Calc 1 that if we see a composition of functions inside our integral, we should be using u-substitution, right? We let u be the inside function. And we recently learned as well that u-substitution is useful for when we have a g prime over g, because that'll integrate to the natural log of absolute g of x. So when you're solving an integral, the first thing you want to look out for is if it's a basic integral. If it is, great, use one of the rules above. If not, look out for a composition of functions and let u be your inside function. Also at that time, look out for a g prime over g and let u be g of x. But now, if it's neither basic nor u-sub, you want to look for a product of functions, and we're going to use integration by parts. So before we talk about the rule for integration by parts, I want to derive it. Because integration by parts is like a product rule for integrals, and it comes from the product rule for derivatives. So here's the product rule for derivatives. And the notation's a little bit different than you probably have seen last time, but I think you'll recognize it. U prime v plus uv prime is equal to the product uv prime. So we're saying the derivative of uv is u prime v plus uv prime. So now I'm just going to do a little math manipulation on this, subtract this over to the other side. uv prime is equal to uv quantity prime minus u prime v. And now, since u or v are functions of x, I'm going to integrate with respect to x everywhere. If we integrate with respect to x here, we have uv prime dx. v prime dx can be written as dv, the same way as in a u substitution, du is u prime dx. So we could write this as u dv. Here we have uv, we take its derivative and then antiderivative, we get back our uv. And here we have u prime v dx, that could be written as v du. So typically we see our integration by parts formula written this way. Integral u dv is equal to uv minus integral v du. Now, how on earth do we apply this? I know that looks very abstract so far. We're going to see an example and we're going to see how to apply it. The thing to look out for here is a product of functions, and you're going to recognize one function as u and one as dv and go from there. So for example, we see this product x times e to the x in our integral. But again, the first thing we look out for, is it a basic integral? No, it's not, because we have a product of two functions there, right? Is it a composition of functions? If so, we would use u-substitution. But we look at it and say, no, there are no compositions here, just a product. And because it's a product, we're going to use integration by parts. So we have to choose one of these factors to be u and the other factor to be dv. Now notice the dx is always going to be part of dv. So I'm going to choose this decomposition for u and dv. We're going to talk about how to choose that a little bit later on. So let's just take a look at this choice. U is equal to x, dv is equal to e to the x dx. Now if this is u dv, what do I need for the other side of this equation here? What am I going to replace this integral with? I need to find v, and I need to find du. So if u is equal to x, du is then going to be dx. If dv is e to the x dx, we want the antiderivative, v is going to be e to the x. So now integration by parts formula says integral of u dv is equal to uv minus integral v du. So let's plug in all the pieces. U times v is x e to the x minus integral of v du, e to the x dx. So we're here. Now notice this integral is easier to solve than the original. We started with x e to the x. Now we just have integral of e to the x. When you see that your integral here is easier to solve than your original, you know you made the right choice of u and dv. So let's continue to solve this, and then we'll take a look at what happens if we make the opposite choice. Antiderivative of e to the x we know is just e to the x, so now we're here, we add on our constant c for integration, and we're done. Of course, to check,
we could always take the derivative here. We can always check our integrals, right, by taking the derivative. Now let's see what would have happened if we used a different choice for u and dv. If we let u equal e to the x and dv be x dx. So u would be e to the x, and then x dx would be dv. So now we'd be here. And again, the integration by parts formula has v and it has du, so we always have to compute from u, take the derivative, get du. From dv, take the antiderivative, get v. So u is equal to e to the x, so du is going to be e to the x dx. dv is x dx, the antiderivative v is going to be x squared over 2. And look what happens when we plug this into the integration by parts formula. We have a v here, we have v and du. Now we notice that this integral is harder to solve than the original. The original had x to the first e to the x. Now we have x squared e to the x. It got worse. This is how you know you made the wrong choice for u and dv. Now I know what you're going to say, well, how do I know how to choose? There's actually a mnemonic to help you remember how you should choose your u. The first thing you want to look out for is logs. If you see any logs, you want to choose that factor for u. If not, look for inverse trig functions. That's going to be u. If not, how about something algebraic like x squared, x to the third plus 1, radical x, something like that. Then trig functions, then exponential functions. Now let's take a look at what we had here. We had x e to the x. So we have an algebraic and we have an exponential. So in this Aliotti mnemonic, what comes first, algebraic or exponential? Algebraic comes first. That tells us choose u equals x. And that's how we know this is the better choice. Okay, so you want to remember your Aliotti guidelines. Now let's take a look at integral x squared ln x. Now let me look at my guidelines. Here the first thing I should be looking out for is logarithms. U should equal ln x here. And that means dv is going to be x squared dx. And as always with integration by parts, we have to compute du and compute v. So du is going to be 1 over x dx, and v is going to be x to the third over 3. Now we're going to plug these into the integration by parts formula, and what does that look like? We have integral x squared ln x dx is equal to uv minus integral v du. So u is equal to ln x, v is x to the third over 3 minus integral v du. du is 1 over x dx. At this point, the most important thing you have to remember is to simplify this first. I can't tell you how many times I've seen students go from here to x to the fourth over 12 times ln absolute x. But remember, if we could do that, we wouldn't be needing integration by parts, right? We have to simplify first. You cannot just integrate each factor. So simplify, we get a negative 1/3 on the outside, right? The negative is here. The 1/3 can come out, and we get x squared. And integrating x squared, much easier than integration we started with. That's x to the third over 3. So now we're here. Now, what would this look like if we had a definite integral? Let's go back up to the top, and let's say we're integrating this from 1 to 2. What would this look like? If we had a 1 and a 2 here, well, how do we note that? Certainly we would have the 1 and the 2 here, but don't forget that this first part has already been integrated. So that gets the evaluation bar with a 1 and a 2. This is saying we took the antiderivative, but we haven't yet plugged in the bounds. So this is the proper way to write this when you have a definite integral that you're solving by integration by parts. So similarly, we have this 1 and 2 here, 1 and 2 here, and now we're here. We're no longer going to have a plus c, but you can then regroup this all together and put the bounds in at once. Regroup all together, get rid of this, put the bounds in at once. Then plug in your 2, plug in your 1, and subtract. Remember that ln of 1 is 0. This term goes away. We're just simplifying here. So now we're here. Let's take a look at another integration by parts problem. Now this one's tricky because we said if it's not a basic integration, we should look for a composition of functions. Clearly this is not a composition of functions, right? There's no function plugged inside another. So it's not going to be a u sub, it's not a g prime over g, but it also doesn't look like a product. And we had been saying that integration by parts is our product rule for antiderivatives. This doesn't really look like a product, but how would I think of using integration by parts for integral of arc sine x? Well, think about the Aliotti Guidelines. Let's go back up to that. What do those guidelines say? Look for logarithms, inverse trig functions. So if I see an inverse trig function, maybe I want to try integration by parts by letting u be arc sine x. If u is equal to arc sine x, then dv must just be 1 dx. It must just be dx. So we're here. And then we can compute du and v to continue with our integration by parts. So even though it doesn't look like a product, technically it is because dv is equal to dx, right? We have 1 here. But really the way you should think about it is think about your Aliotti guidelines, and when you see an inverse trig function, think maybe integration by parts would be useful. So now we're here, we plug into the integration by parts formula. Integral u dv is equal to uv minus integral v du, so we're here. But we notice that we have x over radical 1 minus x squared. That's a typical u substitution problem. But instead of calling it u, because I have u here, I'm going to be proper and call that w. So I'm making a w substitution here. Let w be 1 minus x squared, then dw is negative 2x dx. I need a negative 2 here, a negative 1/2 outside, and we're here. So we take the antiderivative and we're here. These 1/2s cancel. We replace back in terms of x, and that's our solution. Let's take a look at another problem. This one's going to be a repeated by parts. We're going to see what happens. Here we have x squared e to the x dx. We recognize it's not basic, it's not a composition or a g prime over g. It is a product, so we want to use integration by parts. And we take our Aliotti guidelines and they say log, inverse trig, algebraic. We do have an algebraic, that's going to be u. U is going to be x squared, dv is going to be e to the x dx. So du is 2x dx, v is e to the x, and we're here, uv minus integral v du. Simplifying by bringing out that 2, but notice what we have here. This integral is easier than the one we started with, right? We moved down 1 power in x, but it still requires a by parts. So we have to use by parts again. Actually, this is the problem that we started the lesson with. We figured that out already, and if we wanted to do that again, just to show all the work, that's here. That solution goes in here. So our final solution for the given integral then, I'm just going to go from here to simplify. X squared e to the x minus 2x e to the x plus 2 e to the x plus a constant. Lots of times it's convenient to factor out an exponential if you have it all over the place, so we could factor out our e to the x here. And our solution looks like this. Now, for repeated integration by parts, when the derivative of u is eventually 0, there's a shortcut way to do it, a tabular way to do it. So for example, the problem that we just looked at, integral of x squared e to the x, u was equal to x squared, dv was equal to e to the x dx. So what you want to do here, in the case, again, only when u has derivative that's eventually equal to 0 is this useful. What you want to do is list u and its derivatives. So x squared, 2x, 2, 0. We can stop there. Next to that, we're going to list dv and its antiderivatives. In this case, dv is e to the x dx, so the antiderivative is going to be e to the x and e to the x, e to the x. Then you're going to put a plus minus alternating sign. You're always going to start with a plus and just alternate the sign for as many terms as you have, as many lines as you have in your table. And then you're going to go across and down. So our integral x squared e to the x dx is going to be positive x squared times e to the x minus 2x times e to the x. plus 2 e to the x plus a constant. And that's the same answer we got before. Again, this is only useful when u is algebraic with the derivative eventually 0.
Let's take a look at another example. Integral of x to the third cosine x dx. I'd like you to please pause the video and work on this on your own. Now we recognize that it's not a basic integral, it's not a composition of functions, but it is a product of functions, so we want to use integration by parts. And using the Aliotti Guidelines, we realize that we have an algebraic function that should be our u. That's u equals x to the third. And so dv is going to be cosine x dx. So with that, du is 3x squared dx, and v is sine x. So using our integration by parts formula, we have uv minus integral v du. And we recognize here that we have another by parts. We'll take this 3 out and we'll set up another by parts. Again, we have an algebraic function, so u hat is going to be x squared and dv hat is sine x dx. And so du hat is 2x dx and v hat is negative cosine x, and the results of that integration by parts go here. And so here we have our u times v minus integral v du. And we simplify a little bit by distributing our negative 3 here. And we realize once again we have another by parts. Here we'll call this u tilde. U tilde is equal to x, and dv tilde is cosine x dx. And so du tilde is dx and v tilde is sine x. And so the results of that by parts go here. And finally, we can make our integration. And we're here. We have x to the third sine x plus 3x squared cosine x minus 6x sine x minus 6 cosine x plus c. Now, once you realized here that we had u equals x to the third, you might have thought about using the tabular method. And so let's take a look at it that way as well. That's a bit simpler. We have u equals x to the third, dv equals cosine x dx. So here we're going to list u and its derivatives. And here we list dv and its antiderivatives. And then we put our plus, minus, plus, minus, plus. And we go across and down. So we're going to have a positive x to the third multiplied by sine x, plus a negative 3x squared multiplied by negative cosine x, plus a positive 6x multiplied by negative sine x, plus a negative 6 multiplied by cosine x, plus a constant. And so simplifying, we get the same solution we had above. Now let's take a look at what we call a circular by parts.
We have e to the 2x times sine x. Okay, so we recognize that although we do have a composition, a u-substitution wouldn't be sufficient here, right? A u-substitution here wouldn't be sufficient. It wouldn't have anything to do with the sine x. We would still have a product of functions to worry about. So it's definitely going to be an integration by parts. The Aliotti Guidelines say that trig functions come first before exponential, so we should use u equals sine x. And then dv is equal to e to the 2x dx. With that, we compute du, we compute v, and we plug into the integration by parts formula. So we have u times v, that's going to give us this, minus integral v du. Now we're here. We can pull out the 1/2. And then what do we notice again? We have e to the 2x cosine x. This is another by parts. And now we have this u and du and dv and v. And maybe I should call this u hat, du hat, dv hat, v hat. In math, when we run out of symbols, we start just putting like hats and tildes and primes and all sorts of stuff. So just to be proper, I shouldn't call them the same u and v. But anyway, so now we're here. It's another integration by parts. So this is going to be u hat v hat, right? This is u hat v hat minus integral of v du. So we have v hat du hat here, right? So that itself is an integration by parts. This 1/2 pulled on the outside, that's here. So simplifying by distributing the 1/2 through leaves us here. So notice that the integral we started with was e to the 2x sine x, and the integral we have left to solve is e to the 2x sine x. So at first you might think this was useless, but actually it's not. We can definitely get around this. But do notice that this is a circular by parts.
So let's call this integral I, the integral we started with, and then we recognize that this integral, same integral e to the 2x sine x dx, this is going to be I plus a constant. Remember that when we integrate, the results can differ by a constant. So technically, we should call this integral I plus a constant. And so what we have here is I is equal to 1/2 e to the 2x sine x minus 1/4 e to the 2x cosine x minus 1/4 of I plus c. Now, what are we trying to solve for here? We're trying to solve for I. So let's distribute and collect our i's on the left-hand side. So we have I plus 1/4 I, or 5/4 I, is equal to 1/2 e to the 2x sine x minus 1/4 e to the 2x cosine x minus 1/4 c. And again, we're trying to solve for I, so let's multiply both sides by 4/5 and let's distribute that through. And so what we're left with is 2/5 e to the 2x sine x minus 1/5 e to the 2x cosine x, and then let's just call this constant here k. And so that is a solution to the integral. And this is how you work a circular by parts problem. When you see your starting integral show up on the right-hand side, you want to call that I, and here I plus a constant, and then collect your i's to one side and solve for it. And with this, we'll conclude our lesson on integration by parts.